So the first question, as we look at optimizing the pelleting process, is why are you pelletizing? In North America, we pelletize soybean hulls, we pelletize canola meal. In every instance, we are pelletizing primarily to impact the physical characteristics of the product. Take a product that is low density or contains a lot of dust, does not have good material handling characteristics, and turn it into something that is more manageable. Okay? In the case, wrong button again, in the case of pelletizing soybean hulls, it also adds value to the product. Soybean hulls contain everything the soybean contains. It has protein, it has oil, it has fiber. It simply has it in different proportions. Since it has protein, it has the same anti-nutritional characteristics that are in the soybean. Since in most cases the soybean hull is separated at the front end of the process, it doesn't ultimately go through the meal desolventizer toaster, so it doesn't have the benefit of the heating. So in many cases, if we want to make a product from soybean hulls that is going to be more acceptable and suitable for use as a feed ingredient, it needs some heat processing in order to impact those anti-nutritional enzymes. And the conditioning and the mechanical work that we do through the pelleting process does accomplish that treatment, so that we end up with a product that has higher value, plus it's easier to get it from your plant to the customer location. Soybean hulls are very low density. As they exit the process, maybe as low 140, 150, 170 kilos per cubic meter. Very low density, very impractical to utilize that product as it is. If we simply grind the hulls, we can increase the density, double the density or more, but it's still a product that has terrible material handling characteristics, doesn't flow very well, is a very dusty product, and one that frankly still contains anti-nutritional enzymes that make it less attractive as a feed ingredient. If we go through the pelleting process with the heat and the moisture and the mechanical work that goes into it, we create a product that is much higher density, much easier mechanically to handle, to move it from one place to another, eliminate the dust and the fines, and create a product that has enhanced nutritional value. So pelleting really needs to be considered the process. If you want to focus on pelleting and a problem at the pellet mill, you're missing about 60% of what goes into making a pellet. Because most of the factors that will influence the ability to make good pellets take place before the product ever arrives to the pellet mill. So we need a good material, typically ground material. We condition it using steam and or added moisture to get the moisture level up, so that when we compact it through the die, we can compress that material together to make a good quality pellet. Okay? And after the pelleting process, we need to dry and cool those pellets so that they have good shelf life. And the drying and cooling process also impacts the quality, the durability of the pellet themselves. So let's look at each step of this process and see what we need to do in order to optimize the performance from beginning to end. Okay? We're showing the raw material, grinding. Any of you still using this machine in your plants? Yeah, I don't believe so. Separation of ferrous materials is extremely important in the pelleting process, and we'll show you some good examples why. Okay? We condition that product with the addition of steam and moisture, mix it, before we compress it through the die and then complete the process through the drying and cooling. Okay? Particle size. It is important, although not essential, that we size the material prior to the pelleting operation. In all of North and South America, soybean hulls are ground before pelleting. This is intentional. In Europe, it's very common for soybean hulls to go directly from the process to the pellet mill. My European colleagues are more interested in selling pelleting than they are grinding equipment, and so the material goes directly to the pellet mill with no preparation, and by sheer force and determination, that product is compressed, compacted, and forced through the die, and the soybean hull pellets go out. Their efficiency is substantially lower than efficiency pelleting in North America or South America, and the quality of the product that they produce is substantially lower. But it is a different technique, a different way to get to the end product, and that is a common approach in the European market. However, most of us realize the benefit, so we grind the material so that it is at a minimum smaller than the diameter of the pellet mill die hole. So if you're making pellets on a 6 millimeter die, you should be grinding that material through a hammer mill screen of 6 millimeters. That will give you a finished particle that has maximum size, perhaps 1/3 the diameter of that hole. The largest pieces will be 2 millimeters or so, which mean when we go to the downstream processes of conditioning and when we're forcing it through the die, all the pellet mill is doing is forming that material into the pellet, and we're not utilizing the pellet mill as a grinder to reduce the particle size just to make it fit inside of the hole. Okay? It's also important to do some preparation up front and elimination of certain materials. I like the way that Phil expressed it here. Get rid of the die killers. Okay? How many of you in your plants have ever experienced a broken die? Okay. If you're here representing a processing plant, raise your hand because it has happened. Okay? And how many of you, when you examine the die and determine the ultimate failure, realize that it was foreign material that passed through the machine? About 50 or 60% of all die failure is a byproduct of foreign material that goes into the die, stresses the die, and ultimately the die fractures and fails. The good news is that maybe 60% of the pellet mill dies actually get to live a long natural life and give you their full performance. But a substantial percentage of them will die before their time because of improper maintenance or because of foreign material that passes through. What makes a good pellet? Protein makes good pellets. Okay? Protein makes a good pellet. It's easy to form. Protein is essentially plastic. It's glue. We squeeze it through the die, we make a good pellet. Fat doesn't make a good pellet, but it does help material to go through the die. It's a good lubricant. So it helps to have a certain percentage of fat in the material in order to lubricate the die and get it to go through, but it will not contribute to the quality of the pellet. Fiber, at the end of the day, is relatively good for pellet quality because it holds the material in a die. It allows us to generate some compression and some compaction, but it doesn't have a lot of natural adhesive. It doesn't naturally glue things together. So we need to have the protein in the mix from the soybean hull. Soybean itself, soybean hull, well, let's look at this chart. Okay. Soybean meal, good protein, low fat, low fiber, makes a good pellet. Soybean hulls, relatively low protein, relatively low fat, very high fiber, sort of mediocre pelleting performance by itself. Probably the big advantage to soybean hull pelleting in your process, the reason that it's not a challenge for you day in and day out, is the product is very, very consistent. So once you have a pellet mill in operation pelletizing the soybean hulls, you really have very little to think about again until there's enough wear or conditions change dramatically to require an additional input. Because the single ingredient, while it's not easy to pelletize by itself, it's very consistent. Once it's working, it tends to continue to work. Okay? We won't go into the chemistry, and I don't think I have to work very hard to convince you that oil and water don't mix. Okay? When we try to make a pellet out of meal or soybean hulls or sunflower hulls for that matter, we need a certain amount of moisture in the material. The moisture is beneficial for lubricating the product to help it through the die. Moisture is necessary because we're adding steam to condition the product, to add some heat needed in order to make a good pellet out of it. And the product has a certain fat content. So we're trying to put oil and water together in that base material in order to make a good pellet. Oil and water naturally don't want to mix. Okay? Fibrous products don't necessarily accept the moisture very easily. That's the reason grinding is so important, to reduce that particle size to get the surface area so that the temperature and the moisture can penetrate those particles in order to adequately prepare it for the mechanical compression stage of the pelleting operation. The moisture is our conduit. The moisture is the mechanism that allows us to get the heat into the product, and it's also the conduit at the tail end of the process. As we're passing the air over the pellets to remove the heat, the moisture is conducting that heat to the surface of the pellet in order to allow us to get the temperature back down so that we have a pellet finally that will be dry enough and cool enough that you can store it for an acceptable period of time. Okay. In general, the smaller the particle size, the better the performance will be through the pelleting process. And we say this as a rule of thumb. It's not exclusive. It is possible to make the material so fine that we cannot effectively combine the moisture. We can't condition it adding the steam and water because the very small particles will tend to accept more of the moisture. And in the worst case, you actually create little, in the ethanol industry, they call them syrup balls, where the material is coated with moisture, but the internal is dry. So, but for practical purposes, in pelletizing of meal or pelletizing of hulls, the particle size will never be too small. You're not going to put that much energy, that much work into the grinding stage of the operation. Okay? Conditioning. We need to get the product up to an adequate moisture level, and we need to get the product up to a temperature so that when we pass it through the die and put the mechanical forces to compress it through the die, the material can flow together, adhere together, and make a good quality pellet. Particle size is an important part of that operation. The retention time, the residence time in the cooler, is an important part of the total conditioning process. The nature of the ingredients, having more protein, having a product that can absorb the moisture will enhance the quality of the pellet. The quality of the steam and or other liquids that we're adding. Okay? In North America, it's very common to utilize the hull stream as an avenue to get rid of a portion of the wastewater stream. So wastewater will be added back into the hull stream far enough ahead of the process that the hulls have an ability to absorb that moisture so that when we reach the pellet mill, we can utilize steam, finally get the moisture content up around 15 or 16% before passing it through the die. It's very typical for the soybean hull, as it is separated from the soybean and begins its own process through the plant, may be less than 10% moisture. By steam alone, getting the material from ambient temperature, 18 degrees today in Argentina, up to 70 or 75 degrees where we need it to be for efficient pelleting, requires a certain amount of energy input. If we use steam alone, the product will reach the desired temperature before we add sufficient quantity of heat. So we can get the product at 75 degrees, 180 degrees Fahrenheit, by the addition of maybe 3 or 4% steam. If we didn't add water first, we would still have product that was too dry to make a good quality finished pellet. Okay. And again, by proper particle size reduction before the pellet mill, we can do a better job of making sure that that temperature and moisture will penetrate all the way to the core of those particles. A very good quick test for conditioning is grab a sample of material coming from the conditioner, insert a thermometer, and watch the temperature. If you lose more than, in your case, about 1.5 degrees per minute, you know that that material has not been heated all the way through, and you could improve the performance of the pelleting operation by concentrating on the conditioner, being able to hold the material in longer in order to get that product thoroughly heated and thoroughly moistened. The quality of the steam that you use is also important. And almost every instance, CPM will utilize the cost spec valve. Who's the manufacturer? TLV. Sorry about that. See, I'm old. I don't remember things like I used to. TLV manufactures this combination regulator, separator, and trap. Extremely efficient device that gives us high quality, consistent steam going into that pelleting process so that we get the best results all the time. Okay. This was an interesting slide. It said 1 glass of water will stop a 500 horsepower pellet mill. And there, I thought I had a slide illustrating. The way the pellet mill works, we rely on friction between the roller and the die to cause the rollers to turn and cause the pellet mill to continue to operate. A little bit too much moisture means we don't have the friction necessary. The roller stops turning, the material begins to skid, and you get what we see here, a wet choke. And it takes very little upset in the process in order to cause these kinds of problems. Okay. Adding moisture, adding steam, getting the product up to temperature, getting it properly lubricated is very beneficial for the quality of the pellet that we will make. Okay. It reduces the energy consumption because water is acting as a lubricant. It's helping the material to pass through the die, and it's also optimizing the quality of the pellet. We're getting that product up to a temperature where the protein in it can bind together when we pack it through the pellet mill die, and so we end up with a decent finished product. Okay, here's the conditioner itself, and there's a lot of things that you can do by adjusting the pick angles that will influence the conveying action of the conditioner, which will influence the retention time. It's generally desired on lower density materials like the soybean hulls that we end up with the picks or the paddles adjusted very flat so that the material isn't conveyed through. We hold it in as long as possible, allow adequate time for that temperature and moisture to penetrate those particles so that when we do finally put it in the die, we can make that high quality pellet with the best possible characteristics. Okay. And looking at the inlet of the pellet mill, the product enters. There's a port where we can add liquids, water, or in feed manufacturing, we may be adding a little fat, or we may be adding a little molasses. But in the case of soybean hull, maybe a little bit of water to increase the moisture in the product. And then we have our axial steam inlets on the bottom of the conditioner so that the steam will come up through the product. It's going the same direction as the product in the conditioner. Get the best possible commingling between the steam and the product so we have good conditioning before we put that material down into the pellet mill die. Die design itself, we're not going to spend much time on that. This is one that could be a 4-hour lecture just by itself. I won't do that to you today. But die design is very important. The things that we need to consider, the diameter of the pellet, that's important. Your customer has certain requirements and expectations. The effective length of the die, that's the length where the compression is actually taking place. The longer the effective length of the die, the higher the compression ratio, the better the quality of the pellet. However, higher pellet quality requires more horsepower, so the capacity of the equipment will be impacted. Ultimately, the die needs to be strong enough to be able to withstand the forces as the material is compressed and packed through. So the die blank is thicker than the effective thickness or the effective length of the hole, and the rest of that is then bored to a larger diameter to simply provide some relief so that as the pellet leaves the compression portion of the die, there will be some swelling taking place. We don't want that pellet sticking in the relief because that will have negative impact on the performance of the pellet mill capacity, and it may have detrimental effects to the life of the die. That can also become one of those die killers. If the pellets are sticking in the relief, the compression becomes too great, the product can't exit, and so the forces ultimately cause the die to fracture and fail. Ideal conditioning is going to be somewhere in the neighborhood of 70 to 70 degrees. Phil said 12 to 14% moisture, but my own experience is we're probably more in the neighborhood of 15 or 16% moisture in those soybean hulls in order to make a decent quality pellet. For sunflower hulls, we just throw this in here, we end up with slightly lower moisture content. The hulls are naturally a little bit more difficult to pelletize, but if we get too much water in there, then they will slide through the die without any compression, and we end up not being able to make a decent pellet out of it. Okay, here's the key. When you have a pellet mill die and or the rollers worn, take advantage of that opportunity. Look at those parts because they will tell you what's been happening inside of that machine. There was a note in there about the die killer, tramp metal. If you open up the die, and frankly speaking, this is a pretty marvelous looking die inside, with the exception of this metal that has entered the system, plugged some of the holes, okay? And as that die rotates, every time that goes under the roller assembly, there's a significant spike in the energy, there's a significant spike in the stresses in that die, and ultimately that die will fail and break because of the high stress concentrated in the area of the tramp metal. Here's a worn roller. This worn roller has some serious issues. On the adjustment end, where the gear is, this is the front of the pellet mill, we have substantial amount of wear. And on the back of the roller, we have significantly less wear. Okay? Several possibilities exist. Somebody could have used a new roller on a worn die, in which case the roller will take on the pattern of the die. Somebody could have simply had poor roller and die specifications. They need to have more relief on the holes on the inlet side to get more uniform wear. My suspicion is this machine was working with the deflector that was either worn or missing, and there was simply no product being delivered to the back half of the roller, so you had virtually half of the machine that wasn't receiving any feed and as a result wasn't doing any useful work for you. Okay. This one shows just a little bit better, this deflector assembly on the front of the roller support that will take material from that feed cone and deliver it to the second roller. Ordinarily, feeding the first roller is easy. By gravity, the material comes down the feed chute through the feed cone, and we get pretty good feed and pretty good distribution for the first roller. Some of that material is carried by the feed cone. The deflector at the top will then put it onto the second roller, and so it's really essential that we keep the deflector in good condition and properly adjusted so that that second roller is always receiving an adequate amount of feed and doing its fair share amount of the work. The other thing that happens when you have significantly uneven loading on the two rollers is the stress in the die is increased even further. The stress and deflection of the die becomes that much worse. Okay, the deflector assembly at the top. And finally, when you remove the die at the end of its useful life, take a good look at what you're seeing. If you see a shiny area, in this case on the flange where the die clamps, or in this case, the pointer just died, on the wear ring, I'm not quite tall enough to get in front of the projector, on the wear ring up at the, here we go, the wear ring, if you see shiny surfaces, they tell you that the parts have been moving. Moving parts will lead to failure. The die should be clamped. It should not be moving. There should be no wear, no movement or wear in this area, no movement or wear on the back side of the die. Take advantage of that opportunity when the die comes off. In fact, I would recommend, whether it's CPM or not, that you keep the die and rollers together, and whoever supplies those components to you should be asked, should be required to look at them and make sure that you have the best possible combination of roller specifications, die hole specifications, relief and spacing of the hole pattern. That's your one and only opportunity to really evaluate how the machine has been performing from start to finish. When those parts come out, take a look, take advantage. And, okay, last step of the process, the drying and cooling. We're using ambient air to remove the heat and a certain amount of moisture from the pellets. Ordinarily, by ambient air, we can get the pellets down to within about 6 degrees of ambient temperature, and within 0.5% of the moisture level before we started adding the water and the steam. This is within reason. Okay? And there are things that you can do in the pellet dryer cooler to manipulate how much moisture is removed. It's not always necessary or desirable to get down within 0.5% of the initial moisture. If, for example, your hulls were entering the process at 10%, and your trading spec allows you to sell the pellets at 12 or 12.5% moisture, you want to make sure you're giving that moisture to the product. They're going to give you $100 a ton for water. You don't have an easier way in the plant to make money than giving or selling water at the price of meal or the price of the hulls. Okay. Heat is generated in the process through the steam and through the friction, so we have the heat necessary to accomplish our drying. We need air. The air must contact the pellets and it only works on the surface of the pellet. So we need to make sure that we have good distribution of the pellets within the cooler so the air is uniformly contacting everything as it passes through. And ultimately, it takes time for these things to happen. In some industries, they use 4 minutes per millimeter rule that says for every millimeter that moisture and temperature have to move from the core of the pellet to the outside, we need 4 minutes. So if you have a 6 millimeter pellet, 6 millimeter diameter, and it takes 3 millimeters from the center to the core, it takes 3 times 4, 12 minutes retention time minimum to expect that the temperature and the moisture can migrate to the surface of that pellet where the air can carry it away. I don't know if this is a common problem for you pelletizing meal and hulls. It is a common problem in some of our other applications where a customer will have excessive amounts of air very quickly cool the surface of the pellet, dry the surface of the pellet so that the moisture can no longer wick out to the surface where the air can carry it away, and we end up with pellets that are cool and dry on the outside but warm and moist on the inside that don't have good shelf life, don't have good storage life afterwards, simply because of poor management of the dryer cooler part of the process. Air takes the path of least resistance, which simply means we must have good distribution of the bed in that cooler so that we have uniform airflow going through so that everything is evenly contacted. Remember, pelleting is a process. Pelleting is not the pellet mill. Pelleting is grinding, moisture addition, conditioning with steam. Yes, it is the pellet mill, compression, and drying and cooling afterwards. Think of it as a process, and you will find at the end of the day that your plant performance, your results may be improved, and it may not be the pellet mill that needs the attention.
Okay. Thank you.
I'm finished. Thank you.